Hello and welcome back, everybody. Today in calculus, we're looking at something called the alternating series test and also the error bound that goes along with it. So prior to this, again, we have the geometric series test, we have the comparison test, the limit comparison test, and also the integral test. So this is going to be, I think, kind of like the fourth or fifth one right now. So alternating series test, and then there's going to be two more afterwards. Okay, so just to kind of give you like a ballpark as to where we are. All right, so the alternating series test is actually kind of very specific because if you look at all the series that we've been doing so far, all the terms, in order to use those tests, they have to be positive. So what happens if you have a series where your terms are going to be negative, or at least some of them are going to be negative? Then we can't use those tests that we have all the way up until this point. So here is an example of something that I'm talking about. For the time being, we know that the harmonic series right here below, the summation from n is equal to 1 all the way to infinity of 1 over n is going to diverge if you have to add 1 plus 1/2 plus 1/3 plus 1/4 and so on and so on and so on. It turns out that it diverges because we did a comparison test in the past where this is supposedly going to be less than a whole bunch of 1/2s add together. So therefore it diverges. But if we were to take this harmonic series and change it so that it's an alternating harmonic series, then what happens then? So here, my question is, let's go ahead and investigate that alternating harmonic series. So this time we have the summation of n is equal to 1 to infinity of 1 over n, but there's an extra part to it where you have -1 raised to the n power. And so what that does is it takes each term and makes it alternate between positive and negative and so on and so on and so on. And I want to find out what happens if you add up all the terms. Now, geometrically, so you can see what is actually happening here is, let me go ahead and draw kind of like a number line over here, okay? So here's a number line. So here in the middle, I'm just going to go ahead and put 0. If I want the first term, right, s of 1, so then that means that we're going to add -1. So over here, that is going to be -1, so that's going to be s of 1. Now, if I add on the second term to it, which is 1/2, then I am going to go back into the positive direction. So this guy right here, that is going to be s of 2. Then if I add on to the third term, which is going backward to the negative right here, so then that means that's going to be s of 3. And then if we do it one more time, and if I go forward and add on to the 1/4, and that's going to be s of 4 then. So as you can see, what's happening is that each term that you're adding is going to get smaller and smaller and smaller. And this alternation, more specifically, it's actually going to kind of converge somewhere towards some sort of finite value because of this adding of positive and negative number that's getting smaller and smaller and smaller. So it's kind of like zigzagging back and forth. And eventually, it's going to get to somewhere over here then. So that means that it is most likely your answer is going to be convergent as a result, the limit as n approaches towards infinity of s of n. So this is what is known as the alternating series test then. The conditions of using this test are going to be the following. So whenever you use the alternating series test, we can say the following here. Suppose that we have a summation of a sequence. So then this is an alternating series, okay? And by the way, this alternating series thing, it's very specific, right? You have to make sure that it goes from positive to negative to positive to negative and so forth. You can't actually have something like, say, -7 and then +5 +2 +1 and then -7 and so on and so on. It has to go from positive, negative, and so forth. And hence, that's why it's alternating. So if all that setup is there, right, where the series is going to be alternating, we have to have two conditions for it to get the conclusion that I want. If you take a look at each term, right, and it's such the case where, and let me go ahead and get rid of this right here. If you take a look at each term, the absolute value of it, those terms have to get smaller and smaller and smaller. So meaning what you're adding and subtracting is getting closer and closer to 0. So that's condition number 1. And condition number 2 is if you take a look at each term independently, and the absolute value of it is also decreasing because it has to decrease to 0 in this case. So if those conditions are met, then the conclusion, according to the alternating series test, is that the summation of that sequence, a of n, is going to be convergent. Now, note that once again, that all we're doing is we're saying that it's convergent or divergent. We actually don't know what it converges to. So that's the only unfortunate part. But we know that it converges. So, at least that's like halfway there in terms of the battle. Okay, so let's go ahead and try to use this alternating series test for some of these problems underneath right here. So determine underneath over here if the series is going to be convergent or divergent. So one indication that you are going to be using an alternating series test is that you have a part where you have a negative number raised to some exponent. So that tells you that you have an alternation. If you want, you can go ahead and write it out just to kind of, satisfy your curiosity. So for example, if n is equal to 1, you're going to get negative 1/2. And then the next part is going to be plus 1 over 2 squared. And the next part is going to be minus 1 over 8 and then plus 1 over 16 and so on and so on and so on. This part, that's going to tell you that it alternates. So that's the good part. Now, this part right here, that is going to be the rest of it, and that should make sure that it's everything is positive. So let's go ahead and see if it fits all the requirements of what we were saying earlier, okay? So first, what I want to do is I want to find out the limit as n approaches towards infinity of each term. I want to make sure that the terms are getting closer and closer to 0. The absolute value of it anyways. So I'm going to go ahead and say limit as n approaches towards infinity of negative 1 to the nth power, and then we have 1 over 2 to the n. See, right here, that is basically our first part right here. Okay, that's what I want to show. In order to solve for that, well, the nice thing is the alternation, if it's positive or negative, the absolute value is going to kill it off. So what we have now is limit as n approaches towards infinity of 1 over 2 to the n. And that right there does definitely equal to 0. So that means that part 1 of the alternating series condition is met. Now part 2, I want to show that it's decreasing strictly. Well, then what I'm going to do is I'm going to go ahead and say let f of n equal to that part that's not alternating. That's this guy right here. If you recall, in order to show that something is decreasing consistently, the best way is to take its derivative and make sure that for all values of n that we're using are going to be negative for this then. So f prime of n has to be strictly negative. So if I were to take the derivative of this, then that means that f prime of n is going to be equal to, and by the way, if it helps you see this a little bit better, let me kind of rewrite this. This is the same thing as 2 to the power of negative n. So f prime of n, the derivative, is going to be equal to 2 to the power of negative n because it's an exponential function when you take its derivative, multiply by ln of 2, and then multiply by negative 1 because of the chain rule. Okay, so that is going to be my derivative. And this guy right here is definitely going to be less than 0 for all n that is going to be integers that are natural numbers in this case. Okay, so therefore, always decreasing, okay, because the derivative is always going to be positive then. All right, so there you go. We have the first condition, we have the second condition. So then now we can write our conclusion. So by the alternating series test, okay, the summation of negative 1 to the n of 1 over 2 to the n is going to be convergent then. Okay, so there you go. That's how you're going to use it then. All right, so let's go ahead and see for another problem that's similar to it. Okay, so let's see if we can do the same thing. So once again, the first thing is take the limit as n approaches towards infinity of each term individually. Sorry for this one. I think it was supposed to be negative 1 raised to the power of n plus 1. Okay. Now, even though the first term is going to be raised to the power of n plus 1, it really doesn't make a difference. All I care about is that when I throw it in here, this guy is going to make it, the absolute value is going to make it disappear. So really all I care about is just this thing that is over there on the right-hand side. All right, so I need to show that that is equal to 0, okay? So we're going to go ahead and once again get rid of the alternating part because of the absolute value. So that gives me now limit as n approaches towards infinity of e to the 1 over n divided by n. And as n approaches towards infinity, the top part, that's going to give you e to the 0, which is equal to 1, whereas the bottom is going to give you infinity, so therefore it goes to 0, so that part checks out. Number 2, Now I'm going to go ahead and say that f of n is going to be the function where it's e to the 1 over n divided by n. I'm going to take its derivative and then show that it's always going to be positive in this case. Okay, so let's see. If I were to take its derivative, then f prime of n is equal to, we're going to use the quotient rule in this case. So the bottom equation multiplied by the derivative of the top. And then the derivative of the top, there's a chain rule there. And then minus the top equation multiplied by the derivative of the bottom, all divided by the bottom squared. Okay. Let's see. To make our lives a little bit easier, why don't we go ahead and multiply everything by n in this case, because that would allow us to get rid of, let's see, all of those kind of nasty denominators over there. So if we do that, let's see, that is now going to give us the first term. It's going to be negative, and then we have e to the 1 over n. And then for the second part, we also have e to the 1 over n, and then there should be an extra n over there, and all divided by n cubed. And you'll notice that we can factor out a negative e to the 1 over n. That leaves us with 1, and then we have plus n, and then all divided by n cubed. And this guy right here is definitely greater than 0 because remember, n is supposed to be some sort of positive integer. So therefore, this term right here, this term right here is going to be positive. This term right here, that's going to be positive because it's an exponential. This term right here is going to be positive. So with everything that is positive times a negative, I kind of messed up right there. It should be less than 0. So let me go ahead and fix that right there. So there it is. So therefore, it is going to be f of n is decreasing for all n's. Okay, that is going to be a natural number. So once again, therefore, by the alternating series test, then the summation of negative 1 to the power of n plus 1 times e to the negative e to the 1 over n divided by n converges. Okay. All right, cool. So that is basically the basic idea.